give this presentation. So this presentation actually is based on the presentation I and Joris recorded for the International Conference on Machine Learning that this year will take place online. So in this talk, it's meant to be light. There are a lot of illustrations and animations. In the talk, I will present the Boomerang Sampler. I will motivate and define it. And then I will talk about the exact subsampling that probably you already know. And then I will show you some results of the Boomerang Sampler compared to other algorithms. In the second part of the talk, I will present another variant of the Boomerang Sampler, which is called Factorized Boomerang Sampler. We also propose it in this paper, which, by the way, is available online since yesterday on arXiv. And we will use the Factorized Boomerang Sampler for the problem of simulating diffusion bridges, which probably you might be interested on. And finally, I will draw some conclusion. So the Boomerang Sampler, what it is a piecewise deterministic Monte Carlo method. So as any piecewise deterministic Monte Carlo method is a device for sampling from a prescribed target distribution, and is characterized by deterministic dynamics, trajectories, and random switches. The random switches, in this animation, we distinguish two different kinds of random switches. The reflections, which are basically based on the target density or informed by the target density, and the refreshments, which happen homogeneously in the space and somehow are needed for the sampler to explore the full space. Now, what we had in mind when we proposed, when we thought of the Boomerang Sampler, is to reduce the number of Poisson, random switches, because for these algorithms, the random switches, the number of random switches are strictly related with the performance of the sampler. So you see the peculiarity of the Boomerang Sampler compared to the zigzag and the bouncy particle samplers, which are the two samplers, most famous samplers of the family of piecewise deterministic Monte Carlo methods, is that the trajectories are, in this case for the Boomerang, are curved. So they are elliptical trajectories. And in our work, we show that these often help on reducing the number of Poisson random switches, and therefore to improve the performance of the sampler compared to the zigzag and the bouncy particle sampler. So here a table just to collocate somehow the Boomerang Sampler with some other Monte Carlo techniques. So all these Monte Carlo techniques are devices for sampling from a target distribution. And on the left column, you see algorithms which take the reference measure to be the Lebesgue measure. While on the right, there are other algorithms which consider mu0 to be a Gaussian reference measure. So in the first row, you find just the classical Markov chain Monte Carlo methods, while in the second row, we have piecewise deterministic Monte Carlo methods. And here on the bottom right, the Boomerang Sampler. So why are we interested on piecewise deterministic Monte Carlo methods? So first of all, I found very elegant the aspect that this class of algorithms can be simulated exactly, and they are defined in continuous time. And this is somehow an advantage with respect to any diffusion-based method, because if you attended the discussion meeting, you have heard how problematic and delicate it is to simulate diffusion processes in continuous time. While this class of algorithm doesn't have this problem because the dynamics are deterministic and very simple. So another aspect of advantage is that they can also use exact subsampling, like the scale algorithm of yesterday. These make this class of algorithms suitable for big data, so when we have a lot of observation. And finally, these algorithms are non-reversible. Non-reversibility is somehow a property of directionality of the process, and these enhance somehow the convergence properties of the process. On the other hand, why are we interested on Gaussian reference measures? So we would like to try to say high-dimensional settings, and in high-dimensional settings, Gaussian reference measures are more likely and more natural than Lebesgue measures. So there are here a bunch of applications, but of course there are also other. So for example, Gaussian process regression, spatial statistics, Bayesian inverse problems, or what I'm going to talk is the simulation of diffusion bridges, which use a Gaussian reference measure. Plus, if we want actually to go to infinite dimension, then of course the Lebesgue measure does not exist. Finally, we can also express a target density as a perturbation from its Gaussian approximation. And this is what I will do in we are going to do in our benchmark experiments. So here a more formal definition. So the Boomerang sampler, like the other piecewise deterministic Monte Carlo samplers, are defined in an augmented space with position x and velocity v. In this case, when they target a distribution in RD. The distribution, as I said, as reference, Gaussian reference measure mu0. The dynamics of the sampler are the Hamiltonian dynamics, which preserve the Gaussian measure. But they're quite simple, and then also this differential equation can be solved, so they can be simulated at any time without any discretization. And then we have a Poisson clock, which determines the first reflection time, which we call tau. And this is the first event time of a Poisson, inhomogeneous Poisson process with rate lambda. And lambda in this case is given by the maximum of 0 and the inner product between the velocity and the gradient of the potential function. So it's quite similar to the bouncy particle sampler, but in this case, U is the potential function relative to a Gaussian reference measure. And here you can see also the momentum. If you don't know the piecewise deterministic Monte Carlo methods, you see that the directionality of the process, indeed, it is a Poisson rate. So this inner product is takes negative values whenever the process is directed to let's say lower values of the potential U. And when the lambda takes is 0, then there will not be reflections. And at reflection time, we also have this property that the particle, the process, reflect with a standard reflection on the contour of the potential function U. So again, it's very similar to the bouncy particle sampler. So now the reflection time and the reflection rule make sure that the stationary distribution is the correct one. And then we have, as I mentioned before, also some refreshment, which are necessary for the process to be ergodic. And the refreshment are just homogeneous Poisson times with some rate lambda ref. Now, and again, an illustration to see what's happening from maybe implementation level. So after running the algorithm, we have a collection of Poisson event times. Here we distinguish again between reflection and refreshment. And from these Poisson event times, we can reconstruct the trajectories because they are deterministic. Once we have the trajectory, then we take the trajectories, the continuous trajectory as a proxy of the target distribution, or alternatively, we can also discretize this trajectory and take a collection of sample points as a proxy of the target distribution. Now the most delicate part of this algorithm is to draw waiting time or first event time from inhomogeneous Poisson processes with this kind of rate lambda. In order to do that, we in our work, or what is the standard, is to use inversion technique, which means we basically have to find the root tau of this equation, where U is just a uniform random variable. Often this is not possible, so it's also quite normal to use thinning techniques. So thinning, basically, we have to find the upper bounds of this lambda rate, and then we can use this upper bound. We can replace our Poisson rate with the upper bound and simulate from that. As an example, with the boomerang dynamics, given our initial points, the deterministic trajectories, they all move in a compact space. So there always exists a constant upper bound of the Poisson rates. What is the effect of simulating from the upper bound is that we have some more events than what we need. And some events are just, we call them shadow points or shadow events, in which there is no reflection. Basically, the process continues in its direction. So nothing happens. And this is somehow delicate because it can affect the performance of the sampler. Yes, so for exact subsampling, you already know what it is. Here is one slide. So basically, when the gradient of the potential is either intractable or it requires a computational effort, we may take an unbiased estimator of the gradient of the potential. And the magic of the piecewise deterministic Monte Carlo samplers is that we still, although we are not evaluating the gradient exactly, we still have the correct stationary distribution. And then we can also use control variates if we want to reduce the variance of the estimator. So this is the classical example for exact subsampling with big data and IID observations. So basically, we have a target density, which is on the product form. When we take the gradient of the potential, we have a summation of n factors. And instead of having to evaluate the n factor, we can just take one random element of the summation and take it as a proxy for our gradient. As another example, that is going to be the one I use for the diffusion bridges. So it's quite similar. So we have a density which is given by a time integral in this case. And when we take the gradient, we still have a time integral to be evaluated. And usually what is the standard is to evaluate this integral numerically. But with exact subsampling, we can just use a random point inside the range of the integral as a proxy of the integral. Now here there are the results of the boomerang samplers compared with other algorithms. Here we study for the scaling of the algorithm for both the number of dimensions and for the dimensionality. So in the paper we give an informal argument of the order 1 dependence of the complexity on the size of the data, n. And we also show it experimentally with the logistic regression. So in this case, you see the first three box plots are the standard boomerang bouncy particle sample in zigzag, and the latest three are the boomerang bouncy particle sample in zigzag with subsampling. So you see that these three box plots, they do not depend on the size of the data. They don't deteriorate. For the dimension, we also give an heuristic argument for order 1 scaling with respect to the dimension. In practice, it's quite challenging because we also noticed that the Poisson bounding rates, they may affect the performance of the sampler, and here you see that it's not of order 1, but it's still the boomerang sampler is outperforming compared to the bouncy particle sampler and the zigzag. So the boomerang is the right one, the right box plot. Sorry, as a statistics here, I'm taking the average of the effective sample size per second. which is again quite standard for benchmark experiments. So in the second part, here I'm introducing the factorized Boomerang Sampler. So I'm introducing it as compared with the other three samplers that now you know. So here in the first row, we have samplers which have Hamiltonian dynamics, the same dynamics, which preserve the Gaussian measure. So the factorized Boomerang has the same dynamics of the Boomerang sampler. While on the second row, we have zigzag and bouncy particle sampler that again have the same linear dynamics, which preserve the Lebesgue measure. If we instead look at the columns of the table, we have on the left the Boomerang and the bouncy particle sampler. As I explained, they are characterized by one Poisson clock, which determines the reflection, which has the rate lambda. And at reflection, we reflect with a contour reflection. While in the second column, we have what we call the factorized samplers, which basically are characterized by D-independent Poisson clocks with rate lambda 1, lambda 2, up to lambda d. So, and the first event time is the minimum of the D Poisson clocks. And the reflection rule is much simpler. It's just the flipping function, capital Fi, which is simply changing the sign of the height component of the velocity vector, where I is the index of the minimum of the Poisson clocks. So there is a work from Joris Birkens, Kengo Kamatani, and Gareth Roberts, a study of the scaling limits of these algorithms, especially in particular the zigzag and the bouncy particle sampler. And they suggest that the factorized samplers should outperform the non-factorized one in the case of in the high dimensional setting and when there is a relevant conditional independent structure. Now, the core application of the paper is this simulation of diffusion bridges. Here we consider one-dimensional diffusion bridges. So for who doesn't know what is a diffusion bridge, is a continuous model which is defined by a stochastic differential equation that you find here. In addition, with two additional conditions, which force the process basically to start at one point u, so at x0 has to be equal to u, and to end up at time capital T in a point v. The simulation problem is important and is used in many applications, but I would say that the most relevant is Bayesian analysis of nonlinear diffusion models with low frequency observations. In this case, we also consider it because it's a challenging setting and it's not trivial because the density in this case is defined in the space of continuous functions. Now, how we did it? So basically, we expanded the diffusion, the path with the Faber-Schauder expansion. In this case, we use the construction of Brownian motion, Levi-Chesielsky construction of Brownian motion, in which that takes a Faber-Schauder basis function, which are here displayed on the left. So there are these head functions, which are parameterized by two indexes, I and j. And I, we also call it level, and basically define the scale of the function. And the higher I, the smaller the support of these functions. In j, the location. X, ij's are all the coefficients of the expansion. So the Levi-Chesielsky construction of Brownian motion, what does it say? Which is basically if we assume xij's to be IAD, Gaussian normal random variables, then we construct approximated Brownian motion xn, and this xn converges to the real Brownian motion as n goes to infinity, and the convergence is almost surely and uniformly on T. And in this case also, sorry, I forgot to say that V is also a Gaussian IAD Gaussian random variable. And if you see phi hat is the first function, the linear function, which is the only function that takes a non-zero value at the endpoint. So v is actually determines the endpoint of this path. So for constructing Boomerang bridges, we basically fix v to be a value. Now on the bottom right, you see the construction. If we increase the truncation level n, then basically the function has a higher resolution. So this is the black part compared to the red part. And yes, that's it. So the Brownian motion, the Brownian bridge, sorry, will be our reference measure, mu0, that as you have seen is Gaussian. And how do we change measure from the Brownian bridge to the diffusion bridge? We use the Gaussian formula, which determines a change of measure up to constant of proportionality. So for MCMC, it's perfect. And we define the approximated diffusion bridge measure, which is basically the same Gaussian formula that you see here, but instead of evaluating x in the full expansion, we evaluate x in the truncated expansion. Now, in a paper that preliminary paper that we put in arXiv, and this joint work with Frank van der Meulen and Maurice Schauer, we study a little bit this change of measure and how it behaves, and of course we made sure that it converges to the right diffusion bridge measure. And also we discover a conditional independent structure of the coefficients. So when we change measure, the coefficients are not anymore IID Gaussian random variables, but are not necessarily Gaussian and not necessarily independent. But there is quite a relevant conditional independent structure, which is basically implied by the local support of the Faber-Schauder functions. And I wanted to show it with this graph. It's basically the coefficient, for example, if we look at x20 and x22, they are conditionally independent because they don't have a direct edge between the two coefficients, and conditionally on the vertex which point to both the coefficients. So with an edge to both the coefficients. So in this case is x00. Here is the results. So here we run the factorized Boomerang Sampler, and then we extracted 1,000 diffusion bridges from this a diffusion bridge with the drift given by alpha times the sine function, which creates these attraction points at minus pi, 3 pi, etc. So as you can see, is quite a challenging diffusion bridge because it's very nonlinear. So if you naively would propose a Brownian bridge as a proposal for this diffusion bridge, the method wouldn't work. On the right, you see some say performance analysis. So we compare the performance of the zigzag applied for this experiment and the boomerang. So we took as a complexity measure the average number of reflections here on the log scale for each coefficient xij, and on the x-axis we sorted for the index I, so the level of these coefficients. So as you can see, so with the dashed line, we take alpha to be 0. So basically, we are simulating Brownian bridges, and the zigzag, of course, in order to target the reference measure, the Gaussian reference measure, has to reflect many times. So you see the horizontal line, blue line, which corresponds to the zigzag, while the Boomerang sampler does not simulate from the reference measure at almost no cost. Once we change measure, so now for the diffusion bridges, the one on the left, the story is a little bit different. So here both the boomerang and the zigzag have to reflect in order to target this measure. But the absolute continuity between the diffusion bridge and the Brownian bridge makes sure that basically not all the coefficients will substantially change from the reference measure. So you see the solid lines they all both converge to the dashed line, meaning that after a certain level, the coefficients will be approximately IAD, Gaussian random variable. So basically, this experiment is just to say that while the zigzag deteriorates, if we increase the truncation or the resolution of the Brownian, the diffusion bridge, the boomerang sampler does not deteriorate. So we can increase it almost as much as we want. Yes, in conclusion, the boomerang sampler is a piecewise deterministic Monte Carlo method. We can use subsampling, which makes the algorithm suitable for large data. And the Gaussian reference measure makes also the algorithm suitable for high-dimensional problems. Now, we also introduced the factorized boomerang sampler, which takes advantage of the condition-independent structure of the target measure. And we show that the performance of the boomerang sampler for a non-trivial example, which is the diffusion bridge simulation. What are the challenges for the future is definitely to improve the bounding rates of these of the boomerang sampler, because we notice that sometimes the bounding rates can really affect the performance of the sampler. And for the diffusion bridge simulation, so I'm working for generalizing it for multidimensional diffusion bridges, and it should be possible without so many problems. And then what I'm currently doing is studying how the algorithm scales for large T, so time horizon, large N, so for the truncation level, and the dimensionality of the multidimensional bridge diffusion bridges. So that's it. If you have any question, please ask. And these are also the references.
Great, thank you very much. If you want to show your appreciation in the chats, then please do. I don't know whether there's any clapping emojis. There usually are in these things. But if you've got any questions, so if you can put in the chat if you've got a question, it'd be great if you could put your video on and ask it live. But if we kind of order things by what comes up in the chat. So I've got a question in the meantime. I'm sure that hopefully some will come through on the chat. So I'm not completely clear about the last bit, what you were saying about the condition independence and how you're using that.
Yeah.
So can you recap on that a little bit?
Yeah, sure. So we basically propose the factorized Boomerang sampler after referring to the scaling limits results derived by in this paper, which suggests that the factorized Boomerang samplers, the factorized samplers in general, they should outperform the non-factorized one. Well, I didn't really write the implementation, but there is a local implementation which I don't know if you can see the button of this slide in which I put a reference, or maybe yes.
In
which we actually exploit this local structure in the factorized sampler. And yes, so maybe your question was about this graph. I'm not really familiar with the dependencies graph, but yes, in this graph basically says that two coefficients are conditionally independent if they are not directly connected. So here you see that many coefficients are basically conditionally independent, and the condition is on the coefficients which point toward both the coefficients. Is it confusing or?
So I think it's the just because I'm not very familiar with these things, it's exactly how you're exploiting that. So is it just that you're moving one variable at a time, and you only have to care about some of the other variables and that?
No, we are not. No, you move all the variables at the same time. So basically, what is happening is that the Poisson rates in the factorized Boomerang sampler. So we have d lambda rate, lambda 1 up to lambda d. These Poisson rates are not function of all the coefficients, but are function of a sub.
Okay, I get it. Yeah.
And basically, you can use it for making the algorithm more efficient.
Okay, right. Okay, that's fine. Yeah, good. Thank you. Okay, so Yuri has 2 questions.
Hi. So nice talk. Thanks for the talk. So I have 2 questions. Yes. So first of all, so I would expect that this works really well when your target measure is close to a Gaussian in some sense, when it looks like a Gaussian, right? And I'm curious, I mean, I suspect that it doesn't work so well if it's not close to a Gaussian, but you showed also some kind of things that looked multimodal and they seem to work fine. So I mean, if you're far away from the Gaussian, I mean, I suppose you can be multimodal, you can have heavy tails or any different things. Does it then work? Does it still work well, or does it not work so well anymore?
So the only multimodal example we actually carried is a diffusion bridge, and in the coefficient space, actually it is very multimodal. Of course, the multimodality is not in all coefficients; is only in some of the coefficients, because in the limit the coefficients should be Gaussian independent random variables. And for this case, you still get an improvement compared to the zigzag sampler. Of course, if all the dimensions are multimodal and they don't have much to do with the Gaussian reference measure, then probably just a bouncy particle sampler or zigzag, they work the same way.
Okay. And did you try, like, I don't know, heavy-tailed things, for example?
No,
or somehow things that would be different from a Gaussian in a different way.
We just, but for an illustration purpose, we just tried with this artificial target density, which is a high multimodal and different from a Gaussian reference measure, and well, the process still behaves well. Say.
Yeah, it seems to work quite well. Yeah.
Yeah, but it's really we have to study better how the algorithm works.
And then the second question is, I expect that you could repeat the same trick for a different reference measure than Gaussian. I mean, it's not clear why you would want to do that, but I suppose that you could do this. You could repeat the same kind of algorithm if you had a different measure and a different simple dynamics then that preserves it. You could basically do an analogous algorithm. Am I correct?
Yeah, you're correct.
Okay.
So, yeah, the only restriction is to solve the differential equation. So the Hamiltonian dynamics have to be
have to preserve the target measure.
Yeah, the target measure. Yeah.
All right. Thanks. Thank you. Yeah, I guess Mari, you can go ahead.
Hi, thanks for the talk. I think my first question is related to Yuri's first question, actually. So, in this, so how does the regular zigzag and this version differ in terms of the intensity for the heavier tail distributions? Presumably, your intensity would get very large. Sort of your switching intensity gets very large for the heavy-tailed case. And the second thing I had, which was different, I got slightly lost when it came to the diffusion case. So basically, you're checking this. You have this d mu by d mu naught term. Basically, you're checking this every time you have a potential switch. Is that what you're doing? And then you're either accepting or rejecting that switch.
Yeah. So maybe I start from the second question, which I know the answer. So yes. So this is the target density, change of measure, and we use subsampling basically. This is the measure when we take you take the gradient of the log density, then you still have an integral of the gradient of this function fs, and we take basically a random point inside this integral as using subsampling. So the valuation of the gradient here is not of order t, but capital T, but is of order 1. And yeah. The other question we really haven't.
Sorry, presumably you're updating something in your parameter space using your algorithm, and then what you're doing here is this is when you're periodically checking it, or is this completely crazy what I'm saying? That this is to decide whether or not to accept or reject a switch move.
Yes.
Is it?
Yeah. So yeah, subsampling basically works. So we have an upper bound also of these gradients, and then we simulate the Poisson waiting time from the upper bound, and then we check whether to switch or not based on this random evaluation of the gradient. Did I answer the second question?
Yeah. Yeah.
Okay. So the first question, I really don't know the answer. We haven't tried. I also haven't worked for heavy tail distributions. So it's a good question, and I think that theoretically we should study much better how the Boomerang sampler works in this case.
Okay, thank you.
Welcome.
Okay, do we have any other questions? Okay, go for it, Andy.
Hello. Hi. Thanks for your talk. So yeah, I just had a question about the refreshment. So just to clarify, I think I may have missed it because my internet was bad at the start. So the refreshment, is that just at a constant rate? And,
yeah.
And was the point, is it, so the problem without refreshment is that do you become reducible? Is that the problem?
Yeah. So also this aspect we really didn't study in details and theoretically, but yes. So if you don't take any refreshment, then you might have, for example, if you take the potential to be 0, so you want to target from the from a Gaussian measure, then what happens with the Boomerang sampler is that it starts having this elliptical dynamics. And then never, so it's not exploring the space, basically. It's just going around and around, circling around in this elliptic orbit. And the refreshment makes sure that the orbit changes. Mm. So if the potential is positive, maybe, I don't know, maybe you don't need them, but I really don't know.
Mm. So I guess the obvious question then is how did you choose the parameter, the refreshment?
Yeah, so just a visual check.
Okay.
But yes, it's not clear. Theoretically, we didn't really study how to tune these parameters. So I think there is some work on the bouncy particle sampler, but yes, still have to be studied.
Okay, thank you.
Okay, do we have any other questions? Just give it a minute in case people are typing. Okay. It doesn't look like it. So in that case, we can all thank our speaker again. Thanks very much for the talk.
Thank you.